10, 9, ignition sequence start. 6, 5, 4, 3, 2, 1, 0. All engine running. Liftoff.
The objective of a rocket this year is to take an 8.8-pound payload to 10,000 feet using a commercial off-the-shelf motor.
In order to make our goals happen, we are using both some new technologies that we've developed here at BYU Rocketry, as well as some old tried and true methods that we've used in the past. Some of those old methods include the airframe, our carbon fiber body tubes, which have been all built by the students here at BYU Rocketry. We've gotten a lot of experience doing that. Also is the payload deployment system, which holds the payload safely in place during the flight of the rocket and ejects it away from the rocket at apogee. Second is the air brake system, which will control the apogee of the rocket during the coast phase after motor burnout. Then third of all is the fin can, which holds the fins in place using aluminum brackets that we've designed here in-house. Using these new technologies as well as the old tried and true methods, we feel confident that this rocket will fly us to first place in the competition.
The rocket has a fiberglass nose cone filament wound that's pre-manufactured. The body tubes, tail cone, and motor mount tube are all manufactured by us using carbon fiber. The carbon fiber pieces had successive layers of epoxy applied and then sanded smooth until the surface finish was good enough for the rocket. And then a final clear coat was applied, clear coat of epoxy, so that the fibers in the final aesthetic layer of the tubes were able to show through. And on the tail cone, also cut apart and then cut to the correct dimensions, as it was an odd geometry, so it was made a little bit larger. All the tubes are combined with blue tube couplers, and then the switch bands are pieces from the body tubes that were cut off because they were made too long. The rocket fins are made from G10 fiberglass. They were cut on the CNC milling machine. They are secured to the rocket via 6 screws using the fin can design, which is made from 4 pieces of bent aluminum sheet metal, and the fin can pieces were then epoxied into the motor mount section of the body tube. The motor mount tube is held in place by centering rings, which are epoxied in place. The centering rings and bulkheads of the rocket are laser cut with the bolt holes and other hardware attachment points already cut into the wood to save in assembly time and increase precision. The rail buttons on the rocket are made from brass and were cut on a lathe. The whole rocket was painted with primer and then sanded smooth, and then colored coats for the various sections were applied. And then once the vinyl logos and lettering were put onto the rocket, a final clear coat was put over all the painted parts to preserve the surface finish and keep the vinyl from coming off.
I'm going to be explaining a little bit about the concept of operations for our rocket for Sundance. Our rocket goes through 5 major phases through its operation. We have standby mode when we're on the launch pad and ready to go. We have easy access ports on our rocket for us to turn on our electronics and all of our systems so that we can easily enable all our functions and have things ready to go quickly. Once we have ignition, we'll have liftoff and we'll enter the main boost phase. During that phase, all of our electronic systems are gathering data and on standby for operation further in later stages of flight. Once we have main engine cutoff, we then go into our glide phase. And during glide phase, we have our air brake systems actively being controlled and monitoring our predicted apogee through accelerometers and altimeters in order to predict where we're going to end up and adjust that by deploying our air brake system to increase the drag and bring our apogee down to exactly 10,000 feet. Once we have reached apogee, we'll then enter our drogue descent phase, which will be triggered by having our avionics send signals to black powder charges in our upper section of our rocket, which will then separate at the nose and deploy our payload and our drogue parachute, which will help us descend at around 50 feet per second until we reach about 1,000 feet AGL, which is when we'll enter our main descent phase. And we'll have another signal sent to deploy another black powder charge into our main parachute bay and separate and have our main parachute deploy and descend at around 19 feet per second from 1,000 feet AGL to when we hit ground. Then we'll be able to track the GPS signals, go recover the rocket, gather our data, and make sure everything's good to go.
BYU Rocketry has developed several payloads with the objective of developing and demonstrating the CubeSat technologies used for orientation and propulsion in orbit. The last few years, the payload has been dedicated to demonstrating cold gas propulsion. The development of this technology would allow for a CubeSat translation. This year's payload team chose to develop a reaction wheel control system. This system demonstrates the ability to control orientation. Specifically, the reaction wheel payload had 2 mission objectives. The first occurred shortly after the deployment of the payload from the rocket at apogee. Falling under its own parachutes, the reaction wheels would be used to orient the payload to face towards the also descending rocket. This required the development of a system for location communication between the rocket and payload. This system, the sides of the payload, has a single wheel with the ability to extend. However, we couldn't guarantee that the payload would land on the correct side. We could attempt to land on the correct side by orienting the payload to face the direction it was traveling in the correct orientation. However, we couldn't guarantee that we would land on the correct side. Therefore, a braking system was developed and placed on one of the reaction wheels. After spinning this reaction wheel up to a high speed, the brake would almost instantaneously stop the reaction wheel. This braking motion causes a high impulse force that allows the payload to flip from side to side. Once on the correct side, the reaction wheels are used to balance as the wheel is extended below the payload. Using a LiDAR system, the payload continues to maintain balance as it drives around to explore its landing location. These missions demonstrate the ability to control orientation using reaction wheels. Combined with the previously mentioned cold gas propulsion payload architectures, BYU Rocketry could in the future develop a CubeSat with the full ability to translate and orient itself on an orbital mission. We are BYU Rocketry.
are BYU Rocketry.